Another challenge in generative modeling is overfitting. If a model simply memorizes the training data, it might reproduce exact or near exact copies of training examples. This is undesirable because the goal is to generalize the underlying distribution, not to store and replay data. Techniques such as regularization, dropout, data augmentation, and careful dataset curation help reduce overfitting. Large models trained on massive datasets tend to generalize better, but they can still exhibit memorization of rare or unique sequences. Scaling laws have played a significant role in recent advances in generative models, especially in language modeling. Empirical studies have shown that model performance often improves predictably as a function of model size, dataset size, and compute. As we increase the number of parameters, provide more data, and train longer, we often observe smooth improvements in metrics such as loss or perplexity. This has motivated the development of very large models with billions or even trillions of parameters. However, scaling also introduces challenges in terms of training cost, inference latency, and environmental impact. The training process for large generative models typically involves distributed computing across many GPUs or specialized accelerators. Techniques such as data parallelism, model parallelism, and pipeline parallelism allow the workload to be split across devices. Optimization algorithms such as ADAM or its variants are used to update parameters based on gradients computed through backpropagation. Careful tuning of learning rates, batch sizes, and regularization strategies is crucial for stable training. In diffusion and GAN models, additional considerations such as noise schedules or discriminator balance further complicate training. Generative models also raise important questions about representation learning. In many cases, the intermediate representations learned by generative models are highly informative. For example, the latent space of a VA may capture meaningful factors of variation. The hidden states of a transformer language model encode syntactic and semantic information about text. These representations can be reused for downstream tasks, either by fine-tuning the entire model or by using the model as a feature extractor. This transfer learning capability has been one of the key drivers of practical success. Fine-tuning is the process of taking a pre-trained generative model and adapting it to a specific task or domain. In language models, fine-tuning may involve supervised learning on labeled data, reinforcement learning from human feedback, or instruction tuning. Reinforcement learning from human feedback typically involves collecting preference data where humans rank model outputs. A reward model is trained to predict these preferences, and the language model is further optimized to maximize the reward. This process aligns the model's outputs more closely with human expectations. Conditional generation is another important extension. Instead of generating arbitrary samples from the data distribution, we may want to condition generation on some input. For example, in text-to-image generation, the model produces images conditioned on a textual prompt. In machine translation, the model generates text in a target language conditioned on text in a source language. This is often achieved by modifying the architecture to incorporate conditioning information, such as concatenating embeddings or using cross-attention mechanisms. Conditional generative models must learn not only the data distribution but also the relationship between conditions and outputs. From a theoretical perspective, generative models can be understood as function approximators that parameterize probability distributions. Neural networks with sufficient capacity can approximate complex functions, including the mapping from noise to data or from context to next token distributions. The universal approximation theorem provides some justification for this expressive power, although practical success depends on optimization and architecture design. Implicit generative models, such as GANs, do not explicitly define a likelihood function but define a stochastic process that produces samples. Explicit models, such as autoregressive models and VAs, define tractable likelihoods. There are also connections between generative models and energy-based models. In energy-based models, we define an energy function over data points, and the probability of a data point is proportional to the exponential of negative energy. Training involves lowering the energy of real data and raising the energy of non-data. However, computing the normalization constant, or partition function, is often intractable in high dimensions. Techniques such as contrastive divergence approximate the necessary gradients. While energy-based models were popular in earlier decades, modern deep generative models have largely taken center stage due to their scalability. Ethical and societal implications of generative models cannot be ignored. Because these models can produce highly realistic text, images, audio, and video, they can be used for creative applications but also for misinformation, impersonation, or deepfakes. Training data may contain biases present in society, and generative models can reproduce or amplify these biases. Responsible development requires dataset auditing, bias mitigation strategies, content moderation systems, and transparency about limitations. As generative models become more powerful, governance and policy considerations become increasingly important. Another technical consideration is controllability. While generative models can produce impressive outputs, controlling specific attributes can be challenging. Researchers explore techniques such as latent space manipulation, classifier guidance, and prompt engineering to influence outputs. In language models, prompt engineering involves carefully crafting input text to elicit desired behavior. In diffusion models, guidance techniques adjust the denoising process based on external signals to steer generation toward particular features. Achieving fine-grained, reliable control remains an active area of research. We should also consider the concept of mode coverage. A good generative model should capture all significant modes of the data distribution, meaning it should represent the full diversity of the data. In practice, some models, especially early ones, suffered from mode collapse, where the generator produced limited varieties of outputs despite diversity in the training data. Evaluating diversity and ensuring broad coverage is essential for robust generative performance. Techniques such as mini-batch discrimination or improved training objectives have been proposed to mitigate these issues. In recent years, multimodal generative models have become increasingly important. These models handle multiple types of data simultaneously, such as text and images. By learning joint representations across modalities, they can perform tasks like generating images from text descriptions or describing images in natural language. Training such models requires large datasets of paired examples and architectures capable of integrating heterogeneous information. Cross-attention mechanisms and shared embedding spaces are common design elements. Another dimension is the trade-off between quality and efficiency. Large generative models can produce high-quality outputs but require significant computational resources. For deployment in real-world applications, latency and cost are critical factors. Techniques such as model distillation, quantization, pruning, and knowledge transfer help reduce model size and inference time. In diffusion models, researchers develop accelerated sampling methods to reduce the number of denoising steps. Balancing performance with practicality is an engineering challenge. We can also examine generative models from an information theoretic perspective. The goal of modeling a data distribution is related to minimizing the cross-entropy between the model distribution and the true distribution. When training with maximum likelihood, we effectively minimize the Kullback-Leibler divergence from the data distribution to the model distribution. This perspective highlights the asymmetry of certain divergences and explains why some models may prefer covering all modes even at the cost of producing some unrealistic samples, while others may focus on generating sharp but less diverse outputs. The interplay between architecture, objective function, optimization, and data is crucial. No single component guarantees good generative performance. A powerful architecture without sufficient data may overfit. A large dataset without proper regularization may still lead to instability. The choice of objective influences sample quality and diversity. Successful generative modeling requires careful alignment of these elements. In practice, generative models are often integrated into larger systems. For example, a conversational AI system may use a generative language model for response generation but also incorporate retrieval systems to access up-to-date information. A creative design tool may combine a generative image model with user interfaces that allow iterative refinement. The generative model serves as a core engine, but surrounding infrastructure ensures reliability, safety, and usability. Finally, it is useful to reflect on why generative models are so transformative. By learning to approximate the distribution of complex data, they capture deep structural patterns in language, vision, and sound. They shift the paradigm from rule-based systems to data-driven synthesis. Instead of encoding explicit rules for grammar, drawing, or composition, we provide examples and allow the model to internalize patterns. This capability opens possibilities for automation, creativity augmentation, simulation, and scientific modeling. At the same time, generative models are not magic. They are statistical systems trained on large datasets. Their outputs reflect the data and objectives used in training. They do not possess understanding in a human sense but generate outputs by sampling from learned probability distributions. Appreciating both their power and their limitations is essential for responsible and effective use. As we continue to advance generative modeling, we are likely to see improvements in coherence, controllability, efficiency, and alignment with human values. New architectures may unify ideas from autoregressive modeling, latent variable methods, and diffusion processes. Better theoretical understanding may guide objective design and stability. Integration with symbolic reasoning or external tools may enhance reliability. The field remains dynamic and rapidly evolving. In summary, generative models are systems designed to learn the underlying probability distribution of data and to produce new samples that resemble the training data. They rely on principles from probability theory, optimization, neural network design, and large-scale computation. Whether implemented as autoregressive transformers, variational autoencoders, generative adversarial networks, diffusion models, or other variants, they share a common ambition: to model and reproduce the structure of complex, high-dimensional data. Understanding their architecture and working principles requires grasping how they represent distributions, how they are trained, how they generate samples, and how they are evaluated and controlled. With that foundation, we can appreciate both their remarkable capabilities and the challenges that remain. As we continue to advance generative modeling, we are likely to see improvements in coherence, controllability, efficiency, and alignment with human values. New architectures may unify ideas from autoregressive modeling, latent variable methods, and diffusion processes. Better theoretical understanding may guide objective design and stability. Integration with symbolic reasoning or external tools may enhance reliability. The field remains dynamic and rapidly evolving. In summary, generative models are systems designed to learn the underlying probability distribution of data and to produce new samples that resemble the training data. They rely on principles from probability theory, optimization, neural network design, and large-scale computation. Whether implemented as autoregressive transformers, variational autoencoders, generative adversarial networks, diffusion models, or other variants, they share a common ambition: to model and reproduce the structure of complex, high-dimensional data. Understanding their architecture and working principles requires grasping how they represent distributions, how they are trained, how they generate samples, and how they are evaluated and controlled. With that foundation, we can appreciate both their remarkable capabilities and the challenges that remain.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.